record, we can record using some microphone we have.
So this is the interface of the Spread software. So we have two windows. One is Spread Objects and Spread Picture. So to record an audio from here, because we are using this software so that we can edit any kind of audio that we are going to record. Like when we are recording an audio, there might be some silence, noise. So we can just edit that audio from here with this software. Basically, this software is mainly used for like when we are doing some research in signal and audio processing. So to record this video, we have like any kind of audio, we just have to click this new option. And since we are we are recording a mono sound, so this option you have to click. And by default, it's 44,100 hertz. So just let it be like this, and then we click the record button here. Hello, hi. Oh. We just stop, and then we just kind of see. Hello, hi. Yeah. And then we are saving it to the list. So it's being saved here, and then we will have to save it as a .wav file. We are going to use this in the WAV file format. So we are using it like this. And in your desired folder, you just save it here, and then we can import it to our Jupyter notebook, which I already did. So I'm not going to do all these importing and saving file. So I already did this f1.wav file. I already did this before. So we are going to load the audio file here, and after loading, so this is the waveform of my audio. I'm going to just play the audio which I already previously recorded. So this is my recorded audio. The goal of this experiment is to record high-quality speech data for analysis and processing. And this is the waveform of my recorded.
Last line is she audible?
I can turn on the volume, sir.
No, not that line. Whatever you are speaking. You're speaking whether it's audible.
Sorry, sir. So this is the waveform of my recorded audio. And then, but see, if you see the audio that I played, it has some silence in that audio. So right now it's going to remove that silence. In processing. Yeah. Now I'm going to clean the audio. Like basically cleaning means I will remove the audio from.
Go to the top waveform. Waveform you got.
Oh.
Okay. So where is the silence? It's not in the silence. In the beginning you have silence.
Yes. So this is. So these part are the silence part. So like when I'm cleaning the audio, I'll just cut that part using this using this like here. It will start immediately. Goal of this experiment is to record high quality speech data for analysis and processing. So the initial silence is removed in this audio. And then, as we already know that the sampling rate is 44,100 hertz, but still I just wanted to bring that part sampling rate. And now I'm going to experiment when we use different sampling rate with my audio file. Sampling rates are 5,000, 5,000, then 8,000, 15,000, 20,000, 40,000, and 50,000. So if the sampling rate is 5,000 hertz,
Okay.
If the sampling rate is 5,000 hertz, then it would hear like this. So it feels like my voice is in a box.
Sampling frequency we have set in the morning. How many samples we store per second? So actual sampling of recording 44,100 samples. But now we declare that the same audio using only 5,000 samples. What as percentage? 5,000 samples. Lot of information is lost. In the reconstruction of the voice, lot of information is lost. That's what whenever she plays that, it is not being heard as her voice.
Yes.
Play it once again. That is 5,000.
This is 5,000.
Play the last one. Last one is how much?
Last is 50,000. Ours was 44,000.
50,000.
This section is to record high quality switch data or analysis in processing.
Difference you are observing. When some information is lost, what is that information we don't know. But in the perceptual quality of the voice, there's a difference. So sampling rate also plays important role. That's what somebody said. Information loss happened. Then the information loss. Maybe it is while identifying a speaker, it comes into use. Next. So next we are will go with the pitch. We are going to experiment with different pitch. So the thing is, pitch doesn't have any unique, but I'm using like according to what kind of sound we are using. Like musical pitch has a unit called semitones. So I'm using that unit semitones. So I'm going to experiment with different pitches like these -12, -6, -2. So it will the sound will come a bit different. So my original sound was goal of this section is to record high quality switch data analysis in processing. This is the original speed with the original pitch values. So once reduce the pitch, what happens? And once increase the pitch, what happens? So you know what happens if the pitch gets reduced? Slow is speed, that is different. Pitch. Earlier 10 cycles per second are being produced. Now only 4 seconds of cycle. 4 seconds. It's not speed. So what is your opinion about male and female?
Little different from the actual
Little different in what way? Yes.
I mean, it's not her voice.
Female pitch is, let us say, 150 hertz. Now we are playing it to the 80 hertz. It should be like what? It should be like male voice. Because male pitch range is different, female pitch range is different. You are taking the speed sample in female pitch range, playing it with the male pitch range. That is played like a male, isn't it? If it's played 300, how should it be played? Like a child. So that is coming.
Yes. So if it's like -12, like extreme value, it will go 40.
Only my dog is informative.
Yes,
Definitely, you are not saying it as Serena's voice, isn't it? You play the original voice?
yes, sir.
Original.
This section is to record high quality switch data or analysis in processing.
Next one.
Yes.
Next.
Like extreme +12.
It's the next thing one you want to do.
Talking.
Yes, probably not the same thing happen. Just made for the funny purpose, so children will be happy. But it looks like children's speech. Right, next one.
So next, it will be a difference of if we change the amplitude. Like
Amplitude is what? Amplitude is a direct correlate of energy. Energy means loudness. If amplitude is more, you are loud enough. If amplitude is less, your loudness is less. If amplitude is 0, you are muted. Right?
But since I'm using like my Jupyter notebook, I was facing a difficulty in like showcasing like half of my original and twice. So I was using a different software Audacity. So I will just play the audio there itself, because like in our laptops, in our normal system, they just normalize our that voice. So this is a complete audio file where I have I will separate 3 audio files by using a beep sound, and like each in each segment it will showcase like my original sound, half of my the amplitude of my original sound and twice of the amplitude. So if I take this,
So here probably this is an original voice. Isn't it?
yes, this is
This
my.
is an original voice.
Yeah.
This is half the
Half of it.
amplitude.
Yes.
This is double the amplitude.
Yes.
You can see the signal strength also. Along y-axis, what is noted is amplitude. So here amplitude is very less.
Yes.
This one.
This one.
Here it is more. Here it is double.
Double.
That is the energy. How is energy calculated? Energy, amplitude, intensity. How is it calculated? Any EMC question? It is calculated as we take some 20 milliseconds or 10 milliseconds of the speech. Then we take each amplitude, square it, then sum it. That's energy. In that small 10 millisecond segment. Why it is square? If you take simply sum, what happens?
I don't know, I'm not sure it's a negative particle transformation.
Fine, it not be easy only. So then you understand it. So you have positive, some positive values and some negative values.
So it will cancel
what
out.
happens? It cancel out and it becomes zero or something else different. So if you take a square, then we get proper number.
Often something you will take for the
Square will not take it, this square. That's energy is like that.
Find the variance with square.
Energy is a sample square summation in that range. 0 to 10 milliseconds, 0 to 10 milliseconds. Play some sound,
Yes.
give some sound. Increase the sound. Minus 10 of the value, it will be 100. So in that room it was connected. We are then we don't have lab there. Madam, speaker connected ಇದೆಯಾ? Speakers in this room. No speakers.
It is not showing this device is not. So this one is speaker.
Is connected.
No speaker will be on this.
Now it's not.
No, it's this. I think maybe battery may be on.
Change the battery. Keep it near the laptop. Is it connected?
It is not connected.
It is. It is only heard in the laptop.
Yeah, yes.
Mic, microphone. Which high ಮಾಡಿದ್ರೆ It is ನಮ್ಮಲ್ಲಿ ಕೆಲವೊಬ್ಬರು ಈಗ ಜಾಸ್ತಿ ಬಿಸಿರುತ್ತೆ ಕೆಲವೊಬ್ರು ಕಮ್ಮಿ ಅದು ಹಾರ್ಡ್ ಆಗುತ್ತೆ ಈಗ ಗಡಸು ಧ್ವನಿ ಆಗುತ್ತೆ ಈಗ 14 ವರ್ಷದ ಗಂಡು ಮಕ್ಕಳೆಲ್ಲ 18 19 ವರ್ಷ ಇವ್ರ ವಾಯ್ಸ್ ಚೇಂಜ್ ಆಗಿರುತ್ತಲ್ಲ
Connected. It's only one.
It is not speakers. There are speakers out nothing is like that one. ಇದು ಮಾಡಕ್ಕೆ You can continue, so later you can show this is one.
So basically, I wanted to show the difference between how it will here if like we want to change the amplitude. Then the next is I actually extracted vowels from that audio that I recorded, the original audio. I use a toolkit which is known as Track Voice Toolkit. So it will
It's now it's coming.
it's coming.
Please change that. You play the previous one, you play now.
Yes, sir. So this is actually a combination of three separate audio files. It's
Not
not
coming. Is it not for you? On the audio player.
exit because of my password. Maybe often software.
Connected. This time. Start with the beginning.
I think maybe there is some because of that software that I use. I think so.
Okay. Click somewhere in the middle and then play. Now play. Leave it in good place.
So I tried to extract all the vowels from my audio, my original audio. Something
It's a collection of all vowels.
all vowels. And I tried to.
Leave the platform.
Yeah, but I just yeah, it's not coming down.
Once you play that, it's not coming.
Once try that also. So this one is not coming, but this is very visible, isn't it?
Close it and open it one more time. Close this.
No. The MP3 player is it's playing sir.
Let's play.
MP3 player that this is normal player sir. It's playing. Should I play there? But it's in a separate file. So this is the original audio. And now this is the half of the amplitude. Here I think
Here loudness is reduced.
reduced. Yeah.
Double one.
And twice would be this.
This is double the amplitude. Loudness and observing the difference. Yes.
It would have been more better if like I could have showed you in the same audio, but this amplifier.
That is not.
Yeah, it's always it is not. And the next file I wanted to show was the file where I extracted all the vowels, like from that audio file. Like not the vowels I did, I just extracted it. So it's like I used the toolkit in prep itself, and then I extracted this, like this.
Pictures are played.
Yeah, only vowels contained instead of this.
What?
Yeah, obviously. So next we'll see some codes regarding feature extraction. So it's something related to what Sarina has already discussed. So the first thing we have to do is we have to import a library called Librosa. Librosa is a library, Python library, which is used for processing of audio and speech signals. So because we are using all the functions or library functions related to Librosa, we need to import that. Then we just need to call the file names or use the file names where the audio is stored. So I have stored that in .wav format. You can see that. Next one, please. Can you see this?
Yes.
So this is the .wav format. My file name is m1.wav and this is the path name where the file is saved. So audio path m and audio path f are two audio files we are dealing with here. First one is a male audio and second one is a female audio. The file name path I have made it as a raw string, appending it with R. So we are showing R followed by the file path name. Then the next thing what I'm doing is I'm loading the audio file and the file name audio path M and audio path F to the memory. That is done using librosa.load function. So the destination variables are y1 and sr1. Y1 is a numpy array which stores the amplitudes of different samples of the first signal, and sr1 is the sampling rate. So if we are not specifying the sampling rate specifically, it will be 22,050. So when Serena has shown, she has showed it as none. SR is none means in which sampling rate we have recorded, that will be coming to the SR value. By default, in this library, it is used as 22,050. It's around half of 44,100. Then how to play these audio files? We are using the IPD, that is IPython.display library. And this IPD.audio will return a audio player widget from where we can play the audio. So the same audio I have used.
Section is to record high quality speech data for analysis and processing.
And here all the silence before and after the actual audio is removed. And we only have the content. Next is again the file name, the audio content at audio path F, which is a female recording.
For analysis and processing. Goal of this experiment is to record high quality speech data for analysis and processing.
So in both these functions, I have used the file path variable, audio pattern and audio pattern. Otherwise, we can use the vector also, y2 and sampling rate also for playing the audio. So that will also give the same amount. Either the variables, the path name can be used, or the sampling rate and the variable in y2. Next, we are trying to find the shape of y1. So y1 is a vector which contains the amplitude of all the samples in the audio y1, and y2 dot shape will be again the shape of the array where the y2 arrays, the audio signal y2 is stored. So y1 dot shape is 1, 2, 3, 4, 5, 5, and y2 dot shape is 1, 3, 0, 5, 7, 5. The sampling rate is same, which is 22,050, which is the default. Now, how to see the waveforms. So this is waveform 1, which is a male voice, and this is waveform 2.
See the range along y-axis. In case of male, it is up to 1. How many it is?
For male, it is 5.5 around.
along y-axis.
Amplitude, it's 1, -1 to 1, it's normally it's across
minus
-1 to 1.
1 to 1, but for female it is minus 0.4 to plus 0.4.
The amplitude is actually less, going to 0.4 and -4.
Minus 0.4.
Minus-
Energy also you have seen while it is being played, male voice is very loud and female voice is not that much loud. So energy is different.
So
And
in this one, the peak is going till 1, around 1, and
Yes.
here it is going till 0.4.
amplitude is going to those values.
0.4. So this is the way we display the waveforms. So we use Librosa display dot wave show, and the variable name and sampling rate will be given to display the waveforms. Next, how can we extract the audio signals? So mainly we are dealing with pitch. So initially I am showing duration. First one is duration, which that will give the duration of the audio signal. We are using Librosa dot get duration to get the duration of the signal. Then the next feature extracted is pitch. We use Librosa dot PYIN, that is probabilistic YIN algorithm, which is used in the library to extract the pitch values. So F0 will contain the fundamental frequencies over all the samples, and from that, next we can see that F0, we are removing all the NAN, not a number. So when we are taking a signal, there can be not a number values. If it is unvoiced or silence, there may not be a value corresponding to that particular sample. So all such not a number values, NAN, are removed, and we get the pitch values in the variable name pitch values. Then next is RMS energy, which PSR has already mentioned, which is intensity. So intensity across all the samples will be taken and the root mean square is taken. That shows the energy or intensity. Librosa.feature.rms. So that is, and it is taken across all the frames, and we just need it as a vector. That is why we take it as y of 0. Then zero crossing rate is another feature which shows how many number of times the signal crosses the zero line. So this is ZCR. It is done using feature.zero crossing rate. The next one is spectral centroid. It is like center of mass. Where is the most energy concentrated in the particular sample? It is centroid. So all these are taken across all the samples, and so we have a sequence of values. And to see how they change or something, we just take the mean and standard deviation across all the samples.
Whenever I said that a small portion of the speech signal is assumed to be stationary, and we apply all signal processing techniques to that region. So that small portion is called as frame. So here frame has taken is 10 milliseconds probably. So for each 10 millisecond, we get one value, one energy value, one pitch value, like that. So once we plot them, it is called as pitch profile or energy profile. That will help us to decide in what way we are speaking. So that pitch profile and energy profile is that is
coming from.
That
This is
is
the
next.
statistics.
But these are the what are those values? First, increase the
First row is pitch.
Ah.
The first table shows for main.
Mean value of a pitch of first file. First file means male file. That's 173 is the pitch value. And intensity is don't worry about those values. Zero crossing rate also don't worry. Duration is 5.59 seconds. That is male 173 is the average pitch. Come down.
When it comes to female,
For female, average pitch value is 203.
not standing together. 1 second, I'll zoom out, then you can see.
It will go upwards since.
But if you zoom out, we can see. This is fine, right?
Okay. So average pitch value is 203
For female.
for female.
This one
So and energy is 0.06.
for female.
There the energy is 0.1. 0.1 is high energy, 0.04 is low energy. So these will help us to decide whether the person speaking is male or Okay. The next.
So this we are trying to plot that intensity pitch profile.
It's the second part. Anyway. 0.04
Which one, sir?
Mainly 0.04 is the minimum and 0.1 is the maximum.
Intensity. Yeah.
Yeah, intensity. Right.
So this one,
Intensity is 0.107.
this one.
Energy.
That is maximum. Okay.
This is mean and standard
That is not
deviation.
maximum. That's a mean energy.
This is a standard deviation. And for
That is standard
female,
deviation.
this is the mean and this is the standard deviation.
Of many frames we have. The mean of all those values is average of values.
So now we are trying to plot the intensities, pitch, and in the comparison. So this is the pitch of male audio.
It is up to 220. Y axis you can see. Means
Which cone?
I said whenever we speak.